This is our final project for CS4701, and we made 3D Tic Tac Toe. 3D Tic Tac Toe is a two-player game that is similar to the traditional Tic Tac Toe, except that it is played in a 3D space. The layout of our board is shown on the right. We decided to use a board of size 4x4x4 because we quickly found out that the 3x3x3 game was a trivial one. The player who placed their piece in the center had too much of an advantage. So to win in our game, players have to place 4 of their own pieces in a row, column, or diagonal before the other player does. For our AI player, we created a game tree that uses minimax and alpha-beta pruning to determine the best move to make. And finally, we made a desktop application using Java, which will be shown in the demo following these slides. The goals of our project were to first make a challenging but reasonable AI, meaning that the AI should be sufficiently hard for players to play against, and should not take too long to make its decisions. Our next goal was to design and create a GUI that allowed human players to easily visualize the board. It would be very difficult to play this game on a simple console output. And finally, we wanted to take the material that we learned in class and apply it to our project, which allows for deeper understanding and reinforcement of those topics. In this case, it was to integrate minimax and alpha-beta pruning into our AI. The next stage was to start programming 3D Tic Tac Toe. We used a very object-oriented approach to our implementation, and we started by making classes for the framework of our game, which includes class board and class point. In class board, we maintain a 4x4x4 array of integers to represent the game state. There are several functions in the game, 3 of which are listed here. Reset board clears the board, which is useful between games. Set piece plays a player's move on the board, and we call this function after every turn the player makes. We will go into what a point is in the next slide. And finally, check winner loops the entire board to check if there are players with 4 in a row and returns that player. We also check for winner after every turn. Additionally, not shown in this list is the print board function that was very helpful for debugging and test playing the game before creating our GUI. Class point is a small class that essentially wraps the coordinate value of our board. Its main purpose is to make the abstraction of passing in an object rather than 3 integer values in an array. We didn't want to pass in arrays every time a player made a move. Point has a couple helper methods, dot equals and toString, to help with debugging as well. The next step is to code class AI. For our evaluation function, we decided to only assign scores to rows that have a single player's pieces, meaning that the player can actually win on that row. If the AI has 1 piece in the row, it will be weighted a positive 1. If it has 2 pieces, it will be weighted a factor of 10 more, which is 10. 3 pieces is weighted another factor of 10 more, which is 100. And 4 pieces means that the player has won, so we assign maximum integer. Opponents' rows are weighted with corresponding negative numbers. We then summed up these weights across all rows, columns, and diagonals to get the evaluation for the entire game state. Later, we make variations of the evaluation function to test different gameplay strategies. We then started to make the game tree using minimax and alpha-beta pruning algorithms. This is the main logic behind how the AI thinks. We built the tree recursively in a function called minimax that takes in an alpha and beta value, as well as the depth of the tree and whose turn it is. For minimax, we kept track of the current score and the minimum or maximum score depending on which type of node we were at, either in a maximizer node or a minimizer node. These scores are the result from our evaluation function mentioned earlier. To find the best score at the root, we recursed all the way down to a set depth limit, and while coming back up the tree, we alternate between keeping the maximum or minimum value. To optimize searching through the tree, we implemented alpha-beta pruning. Alpha-beta pruning essentially removes all branches of the game tree that the maximizer or minimizer will never get its value from. This happens when the node the level above or the parent node, already has a value that is better than the current child node. So the current node no longer needs to explore the rest of its branches, since it can do nothing more to make the parent choose the current node's value. For the implementation part, we maintain alpha and beta values that get passed through the parameters of the min-and-max function. We update these values by taking the max of the current score in alpha or the min of the current score in beta, depending on the turn value. We make a prune when alpha is greater than or equal to beta by simply returning from the recursive call to stop recursing further down the tree. The final part is to code the GUI for 3D Tic Tac Toe. We first designed the board to be 4 projected planes so that it is easier to see where in the 3D space each box is. Using individual lines from linear equations, we form the trapezoidal planes of the board. We then map the XY coordinate of the mouse click to the position on our 3D board. Since the shapes of the spaces are irregular, we use the equations from our lines and inequalities to figure out which box the mouse click is in. Finally, for the pieces, we decided that spheres would be a good pick because they make the game appear more three-dimensional, and they didn't have to be projected onto the board. The pieces in the back are slightly smaller than the pieces in the front to preserve perspective. To evaluate our AI, we created a few more evaluation functions that altered how our AI played the game. The offensive strategy favors completing its own rows over the opponent's rows, so its own rows are weighted more. The defensive strategy tries to block its opponent's rows before completing its own rows. The balance strategy is our original evaluation function, where both types of rows are weighted equally. And finally, we have a random strategy that selects a randomized valid move. After running our game several times, AI versus AI, we found that the defensive strategy is the strongest one and has the highest chance of winning. Also, we found that random loses to the other strategies essentially every time, which is expected. Finally, we realized that increasing the depth of the tree does not significantly affect how well the AI plays. It does, however, greatly increase the time the AI spends thinking. We think this is because the branching factor for the game is very high, since it starts at 64, which makes it hard to both prune enough branches and also to choose the best move out of a lot of different possible moves. Now we have a demonstration of our 3D tic-tac-toe, where we play one game against the AI.
This is the demo for 3D Tic Tac Toe. I'll be playing against an AI that uses the defensive strategy, which favors blocking my moves instead of creating rows for the AI itself. The Minimax algorithm will be looking 3 steps ahead, so hopefully I do okay. I'm actually quite awful at this game. So let's get into it. So I guess I've ended up tying against the AI. And does that mean I'm just as smart as the computer? You tell me.